Okay, welcome back. So we're having a look now at some closed forms. What is the closed form, this particular one? When does a sequence or a series have a closed form? What is that? Where did that closed form come from? Let's work it out. Let's use technology to help us. So we'll grab Wolfram Alpha. So we've got 1 plus 3 over 2 plus 7 over 4, 15 over 8, I'm just 7 over 4, plus 15 over 8, plus, what else have we got? Should be enough, 31 over 16, but I'll keep going. 31 over 16, plus 63 over 32, plus 127 over 64, this is our sum, isn't it? So we're going to go plus dot dot dot. Let's see what Wolfram says about this particular sequence. Let's see if we've got a sum. Do we have a result? Unable to determine the general term. Have I made a mistake there? 1. Oh, because these are the sums. They're not the value, they're the sums. See that? So it's important that we did do that. So we're filling in the sums. At the first sum it's 1, then it's 1 and 1.5. So this was the one that I wanted to do. So I kind of did this before, which was interesting. So an 8, so we'll get rid of these other terms. So that's good, I'm glad I do that. Some wouldn't be glad I do that, but that's me. Okay, just checking out the values. 1 over 2, 2 over 4, 1 over 4, 1 over 8. Okay. So it converges to 2. We did that earlier. But look at this, a partial sum formula. Very good. 2 to the minus k means it goes underneath. So we've been able to establish a partial sum formula. There you go. That's the one that goes underneath. So can we check this out? Can we see what the partial sum formula is? We could probably do that. Well, one of the ways that we check out whether or not this has a particular value is that we do what's called analysis. And the analysis will ask us to think about this closed form. Okay, what is this particular one? So the closed form that we looked at was this one. So 2 to the minus n, that's all that is, and it's starting from n equals 0. So we just need to be mindful of that. 2 to the n equals 0, 2 to the minus n. So we'll go and have a look at that. And 2 to the minus n. So we've got 2. So this one here can be expressed as the sum of n equals 0 to infinity for 1 over 2 to the n. Okay, that's the sum. So if we do that in Wolfram, which we can do, we can kind of put this all in reverse. And we can say sum 1 divided by 2 to the power n from 1 to infinity. Yeah, I'll pick that one, it's the same one. Okay, so it's converging to 1, and it's given us the same partial sum formula. See that? So this is a really interesting idea of how to develop this. Now this partial sum equation needs to be tested. If n goes to infinity, not just to 7, but it goes to some value k, and k goes to infinity, then what's the value of sk? And it's interchangeable with n and k, so don't be alarmed by that. Okay? Well, one of the things that we can do is we can check the limit. Now, what is a limit? In a maths world, what is a limit? And in the workshop, what I did was I got a person and a chair, and I put the chair at a certain position, and it demonstrated a distance. And I gave the chair a bit of a human, I personified it and gave it a bit of an aura. And so that when that distance became too small, okay, so green's okay when it's here. Nobody was too worried for the chair there. But as soon as we got to the aura, without actually touching it, we came into the space. So at this point here, we're not actually touching the chair, we're just in its space. And the expression I used was ew. Okay? Now the red one is clearly touching. And we make no distinction in our humanity, in our human experience, between a red and an orange. They're both you. In other words, the human experience tells us that invading our personal space is the limit that we're prepared to go to. You've crossed the limit. So you don't actually have to be touching in order for the limit to be found. And so the analogy here is that the number doesn't actually have to be the number. It just has to be infinitesimally close. And the human abstraction close. Okay? And we'll get there. So if we put a 0 and a 1 here, if this distance becomes infinitesimally small, we can clearly say human abstraction small. Human abstraction small. We can say that whatever's on its way is, for all intents and purposes, 1. Even though it's not actually 1. So how do we implement that human abstraction, the idea of a limit, into the algebra? Well, the answer is we use this symbol. Okay? We say n's approaching infinity. And we put the next bit there. So the limit symbol represents all of that thought there, all of those ideas. So we can do this to check out this particular one. So it's a nice little analysis activity, but I wouldn't want you to be overly concerned. I'm not going to suddenly burst you with that. There's a subject called real analysis that you can do as an elective if you want to. That will certainly cover all of this. So if we take the limit as n approaches infinity, we'll use this next week in calculus. So that's good that we got a chance to introduce it. And 2 to the n, so I've gone back to n's now. Not k's, but n's. And we're going to do a bit of a trick here in our gymnastics, because we always do, don't we? Okay, we want to separate the fraction, because this is a minus sign, so we can split this fraction. So we're going to have 2 to the n over 2 to the n minus 1 minus, so it's the same family. So going backwards again, don't you love it? Okay, and this time we're going to do something a bit strange here. Okay, what we're going to do is we're going to say that 2 to the n is the same, is it not, as n plus 1. Hang on a minute, you can't just plus 1. Well, subtract the 1. What? Subtract the 1 plus a 1. Now this one here has an equivalent form. It's 2 to the n, 2 to the 1, 2 to the minus 1. We know this is true. We've seen this in our indices studies. So in actual fact, what we've done is we've been quite tricky. By making this way, we can do some cancellations. Always have to put that in to explain your way. So we're going to have 2 to the n, 2 to the 1, 2 to the minus 1 over 2 to the n, 2 to the minus 1 minus 1 over 2 to the n minus 1. So we can clearly see some of these are going to cancel. So we're going to be left with 2 up there, 2 to the power 1. So the limit as n approaches infinity has in this term a 2 and 1 over 2 to the n minus 1. Now, what happens to this one? As n gets bigger and bigger and bigger, 2 to the n gets bigger and bigger and bigger, but the quotient itself gets smaller and smaller and smaller. Okay, so the quotient itself is eventually going to go to 0. Okay, so a big number on the denominator is a very small number overall. Okay, we can live with that. So all we're left with is the limit as n approaches infinity for the number 2. Well, that doesn't make any sense. Well, it does. N's not involved, so the limit is 2. So we're very happy about that. So this is the partial sum. It's the partial sum limit. It's not the work that I did previously, which was to show the closed form. We need to get our vernacular correct. So the closed form, but the partial sum has a limit. So we can do the limit idea with Wolfram alpha as well. Why not just quickly show that? This might be the Wolfram video. Okay. So what do we have? We have the limit of 2 to the n divided by 2 to the n, where it's minus 1, the limit as n approaches infinity. Let's see what it does. I did it approached, didn't I? Approaches infinity. Let's try again. It did process it, didn't it? So we got the same one using Wolfie. But remember, this is a slightly different idea to the idea of the closed form. Okay, the closed form, but this is just the limit. All right, so what's happening in our graph is that this particular value is coming to 2 for the sum, for the partial sum. Okay, it's coming to the sum, partial sum. So let's put the partial sum, because we don't want to confuse it. And so the partial sum is coming to 2. Okay. Oh, wow. Okay. So just going back to Wolfram for a minute, I just want to go back to the limit of the partial sum. And so get the one more. That's the sum of the actual convergent closed form for our particular one, which is 1. So we need to be very clear about what it is that we're talking about when we do these. So with a bit of experience, you'll find that you'll be able to make distinctions between partial sums and convergences and the like. Okay, there it is there. It's coming to 2 as a partial sum. Okay, and the previous one. So that's the beauty of just loading these things up. The closed form went to 1 and the partial sum went to 2. So that's a nice distinction that we need to make. All right, so what I might do is stop that one there and come back for the use of this particular one here. Be back soon.